Now we can create the drivers and the application files and programs and place them on the microblaze. And the program that will allow us to do this is called Vitis. It used to be called SDK, and Xilinx has revamped it and created a new software. They're both based on Eclipse. But anyway, so the minute you actually open that Vitis software, you can actually go and look for it. It's going to be under Xilinx in here, along with the other stuff that you have, Vitis IDE. Okay, so you're gonna see that you'll be greeted with the thing that basically tells you to create a workspace that will save all your information. We're gonna do that. We're gonna launch it, and at this point I can really close Vivado, but I'm not gonna, because I'll have to go back to it in a few minutes. Okay, so the first thing you're going to be facing is a welcome message. You can either create an application project from here, or I'm going to show you from a different place, which is here, File, New, and you can say application project. And this application, we're going to call it Vanilla Test, for example, and we're going to go next. And then from here, you can select the platform, this one here that came with Vivado or from Xilinx. But what we really did is we have exported a file which is an XSA. That's what we're going to be using. So we're going to create a new platform, and it's based on the SoC that we have just created. So we're going to have to add it because it's none of these ones in default. And then we're going to go to my Vivado projects. I'm going to go to that particular project, the Vivado one, and you're going to see that in the home directory, you're going to see that this XSA has been created. So you double click on that, and now you have it. So next, it actually realized that it's a microblaze project. It allows me to actually put a FreeTOS, some sort of an operating system, but we're not going to do that. We're just going to keep it as a standalone because we're programming in a bare metal style. Then we're going to say that the language of choice is C++ because we're using classes as drivers. Next, and then we're going to create it with an empty application. Then we'll wait for a couple of seconds, and you're going to see that things are being generated in here. And these things are actually a couple of categories. The first one is the hardware level or hardware related code, and this is basically in here. You can see that here, the top vanilla, so you can see actually the Bitstream got imported. Frankly speaking, you can see the Bitstream and the MMI, which we're going to refer to shortly. And it has all the information, the board support package, the hardware specification, for example, the one that tells me how big is that microblaze, for example, how much memory we have. Remember, it's like everything is through the wizard for the microblaze, so you can actually you can configure it the way you want it. So as an application, you need to know how much memory you have and whatnot, and what type of options did you actually turn on. So all of this have been done for me by just importing that XSA. Next, you're going to see that I have an application. This is actually exactly like you have done whenever you programmed in C. It's just an application. It expects some sources. If you double click in here, you're going to see that there's a README that tells you it's an empty application. You need to add your own sources. So we're going to add them in here. I'm going to provide you with a bunch of files. So we're going to do this here, and we're going to say import sources, and we're going to browse to it. So after browsing to it, you're going to see that I have split the C code into drivers and applications. So you can see the drivers in here. We click select folder, and it gives me all these files. We're just going to select all of them and add them. And we're going to also, so these are just the drivers. So let me talk about them before I actually add the program itself. So the drivers, as you probably remember, we need something for the timer. Here's the timer. And again, they're .h and .cpp because I'm separating the implementation from the interface. So I have the timer. I have one for the UART. I have one, well, the general purpose input and output, we have decided to combine them into one because they're pretty simple. And of course, we do have some sort of a map that tells me what slot is connected to what. And I have something with the read and write that gives me all the macros to read and write. And these are actually utility routines in here, and I'll talk about them briefly. So again, if you're interested in figuring out like what type of interface or what type of information you can actually utilize that drivers for, you can just double click on the header file and just read it. So this one here is for the GPIO, which is the input and output. You can see that it has the input core, and the input core, as we have seen, it has the read in it, or maybe read 1 bit. And as well, this is very special because they're pretty small. You can see that the GPO core is also included in here. Some of these drivers are a little bit more complicated. This one here also has something to do with the pulse width modulation, which we're going to get to later. But what I want to mention is the UART is a little bit more complicated. You do have a lot more functions in here, and you can read these documentation and read the comments to figure out what they do. For example, the display is going to mimic what printf in C does, which you probably have seen as something similar as cout or print in Python and whatnot. And you can see that you have that function is overloaded, so you have a bunch of options for it. So read the documentation and see what it's actually doing. UART is very useful in displaying debug messages on the console here. Okay, so let me just talk briefly about this particular file. This particular file is a helper file. This is actually the routine files that we have showed you in the figure. Let me show you that figure. So in this figure, what you do see is we have done the hardware. We have just added the driver files. We did not put anything in the application yet. Everything is a driver, but I have added from the application, I have added these utility routines, and these are what these files are. So these files just import other files and provide me with really specific specific functionalities, which is specifically console display functions, timing functions, debugging functions, bit manipulation macros. So let's take a look at the code of CD. So you can see in here, it's actually have that tells me that the timer slot and the UART is connected in here and so forth. But what I'm more interested in is, you can read the details later, but what I'm really interested in is these helper functions. So this one here now in microsecond tells me the current system time in microsecond, and it tells me that in millisecond, and it tells me like, oh, you can make the processor sleep for a few microseconds or a few milliseconds. And there's a lot more as well with the debug with the UART. It's actually, the debug is really interesting because you can actually place certain debug code within your actual code and turn it off and on pretty easily. And I'm going to show you that when we talk about the application. And also you can see in that, within that particular file, you can see that I have the bit manipulations from C, the one we've seen before. So these utility routines are really useful, and they do expect the timer to be in slot 0 and the UART in slot 1. Other than that, the rest of the slots, basically the 62 other slots, you can actually put whatever you want in them. Alright, so now we do add the other application. For example, we just added the drivers, so we need to actually add the application. So let's do that. So we're going to add the application. We're going to browse in here. We're going to go up one level, and I have placed the application here. It's actually one file, and you can see that here. So the application is in here, and that's basically, we're going to go through it in a separate video. But as you can see very briefly within its main, it actually does a timer check, an LED check, and switch check, and a UART check. I'm basically the I/O modules I instantiated in this vanilla subsystem or vanilla system. Basically, I'm just utilizing it. So now, as any other C code, what you need to do is you need to debug it and wait for it to actually compile. And then after it compiles, what you need to do is you need to load it on the FPGA board. And of course, you don't load a C program on the FPGA board. You load a bit file that also has the C code in it. So now that the build has finished, you can see now we can actually load that particular function on the FPGA. So let me show you that. So you're going to go to Xilinx in here. You can say, hey, program FPGA. And now you're going to see that the bit file is already included in here. That's because when we added the XSA file, when we exported it in Vivado, we said, hey, include the bit file in it. So it's already in here. And we're going to leave everything as is now, except for the microblaze. The program is actually that .elf file that we just compiled, the vanilla test.elf file. Okay. So we're going to do this. We're going to create a program. And as it turns out that there will be an error in here. This error is old. It used to be in the SDK, in older versions of the SDK, and it appeared again. But there's a couple of hacks around it, so I'm going to show you these hacks. So the error we get in here, it tells me invalid processor specification because it's seeing this as opposed to that in here, or it's expecting this as opposed to this particular term. So let me show you what we do. So the hack around that I found is actually, you're going to go to the hardware files here, the hardware specification files. We're going to go to the hardware, and we're going to go to the MMI. So the MMI file here tells me everything about that processor. So it tells me, well, you can read these information, but for example, the one that is relevant to us right now, it tells me the NDNS is little, and it tells me that the inst path, this is actually where the error is coming from. It has the inst/microblaze. So we're going to just remove that. We're going to save it, and now we will be able to program the FPGA. When you're reading, you probably are going to see that this is generated by Vivado, this particular version, at this particular time and whatnot. And anyway, and it tells you do not edit this file, just ignore it. We're going to edit it so that it works because there's a bug in here. So we're going to save that in here, and now we can actually go to Xilinx. We can say program FPGA, And this one here happened to be, this is the MMI file, and as it turns out it's cached. So what you need to do is actually you need to browse for it. So this is within my Vitis workspace. So we're gonna go to the top vanilla in here, and inside it there's actually hardware, and it's cannot see it because of the BMM. What I have is I have an MMI file. So we're gonna do this, we double click there, and now we can actually say program, and you're gonna see that the FPGA is going to be programmed. So the FPGA has just been programmed, and you can see the actual test pattern and the test code that I have is now running on that FPGA. Okay, so that's pretty neat and pretty convenient. Again, this is just one hack, and it now allows me to program that particular FPGA. So it's really neat because I did not need any Vivado to load it or wait for it pretty quickly. Now I'm writing C code as if I'm actually programming a microcontroller. Frankly speaking, you are programming a microcontroller. It's just part of a bigger system that you're controlling. So for example, if you decided not to test the timer and not to test the LEDs and not to test the UART, just the switch checks, for example, we're going to leave that debug for later. You can just save it, build the whole program, and now you can actually, after it finishes, you can see that it's pretty simple to upload that code in here. We're going to program the FPGA. We're going to say program, and it programmed it. You do not have to wait and generate the bitstream all over again and wait for it forever to actually finish. It's pretty quick. So this one here is a little bit, it might seem a little bit on the slower side, because what it's doing is actually taking the bitstream that we already generated in Vivado, putting that code on top of it, and just loading it to the FPGA. And as you can see on the FPGA now, I only have one of the tests running. Okay. So before I close, I want to show you the other hack because it might be useful. So the other hack is the following. So after you compile this file, you have created something called a .l file. You can technically go to Vivado, and in Vivado, you can actually go in here and you can say, hey, I want to associate an L file in here, and you can actually go and browse for that particular L file wherever your Vitis is. So this is my Vitis workspace. Let me just show you here. That's the home of the workspace. You can actually go to I believe it's vanilla test, and then debug, and then here you can see that the vanilla test in here, that's the L file. We're going to do that, and we're going to say okay. And now my microblaze here for the CPU, it's doing that. You can do the same thing for the simulation. For some reason, if you're simulating the processor after it gets programmed, you can actually do this. I'll just leave these by default, which basically tells me that for simulation the processor is going to be empty. We're going to click OK, and now what you're going to do is you will see a message that tells you that the right bitstream is out of date. You can actually regenerate that bitstream and click OK. And now the bitstream that will get generated is actually a bitstream that has the hardware and also the program that we just compiled in Vitis. So whenever you actually program the FPGA from here, it will have it. And the reason why you might have this one or this method, it might be just a solution for that problem that we had. But also you might just take that bit file and save it on the FPGA or save it on an SD card or something like that you need. It actually has the code, the hardware code and the software code together in the same exact file.